In this online lecture, we are going to study about thermochemistry. So, it is the study of energy changes that accompany physical or chemical changes in matter or chemical. Now, what do we understand by physical change? Now, by physical change, we understand, for example, water converting from gaseous state to liquid state. For example, in condensation. So water is from the gaseous form, the water vapors, they convert into liquid droplets on, let's say, on a surface of a ice cold water containing this glass is containing ice cold water. So what will happen? So the droplets of water will be observed here on the surface. So what is happening? The water vapors, they are condensing to form the liquid. So what is happening here? So the molecular formula is same for water. It was previously also H2O. Here also it is H2O. But what is happening from the gaseous state, it is converting to liquid state. Only the physical change is happening. Okay. So its physical state is changing. Firstly, it was existing as gas. Now it is existing as liquid. Now, what do we understand by chemical change? So chemical change is essentially, for example, nitrogen plus oxygen is combining to form NO. Okay, so what is happening here? These two reactants are forming a product whose molecular formula is entirely different from its reactants. So what is happening? This is known as a chemical change. So this is referred to as a chemical change, where actually the molecular formula, molecular structure, it changes. Now, when these processes happen, either it's physical change or it's chemical change. So what are the energy changes that are involved in this? So what are the energy changes that are involved either in chemical change or in physical change? So the study that deals with it, that branch of chemistry is known as thermochemistry. I hope that's clear. Now, moving on, first let's do some revision of some basic terminologies. I'm sure you must be knowing about that. So let's first of all know about energy. So what is energy? Energy is the ability to do work. What are the units? So the SI units are joules. Okay, the SI units are joules. Its symbol is G, uppercase G. Now, energy is the ability to do work. If you feel energetic, you will be in a good mood. You will want to do a lot of work, right? Now, energy is categorized into two categories depending upon its position. So, potential energy, and then the second is kinetic energy. So, potential energy, this is energy possessed by virtue of position. So let's say you are sitting right now. So the energy you're possessing right now is by virtue of your position, and that energy is referred to as potential energy. Okay. Um, Position, or you can also say composition. Okay. So the water, let's say it is filled in a tank, and this tank is lying at the top of a building. So this water is possessing energy. It is having some position, so the energy it is possessing is known as potential energy. The second thing is kinetic energy. The second form of energy is kinetic energy. Here, the energy is due to motion. So an object that possesses kinetic energy, it is by virtue of its motion. It is because it is moving. For example, this water, you open the tap here somewhere in the building, and then this water starts to flow through the tap. Now, what is happening? The water is running down, it is doing some motion. Okay, so the energy possessed by this running water is known as kinetic energy. Let's say you start moving, then the energy you will possess is known as kinetic energy. Now, apart from energy, some other terminologies which you should be familiar with while studying thermochemistry is thermal energy. Now, what do we understand by thermal energy? The total quantity of the total quantity of potential and kinetic energy. So I will write potential energy as PE and kinetic energy as KE in a substance, or you can say for an object. So what is thermal energy? It is the sum total of potential energy and kinetic energy in a substance. The another term you must be familiar with is heat. What is heat? It's the transfer of thermal energy from a warm object to a cooler object. Okay, so let's say the temperature is very, very low outside. Okay, your hands are cold, and then you go and buy a coffee from a shop, and you hold that cup of coffee in your hand. So what will happen? So this coffee is warm, your hand is cold, so the heat will flow from the coffee towards your hand, and in some time your hands will become warm. So what is happening here? This is known as the flow of thermal energy. So the thermal energy is flowing from coffee towards your hand. So this is known as heat. Next is temperature. What is temperature? Since we are dealing with thermochemistry, so this is what we want to also know. Temperature is a measure of the average kinetic energy. Now, why do we use this term average kinetic energy? I will write Ke of entities. I will go into the details in a minute. In a substance. So, what is temperature? It's a measure of the average kinetic energy. For example, here is a room filled with a gas. This gas will have a lot of atoms. Okay, so you know already 1 mole consists of how many? 6.023 into 10 to the power 23 atoms. So these many atoms exist in 1 mole. So what we are trying to say here is that, let's say you capture 1 mole of gas particles in a closed room. So what will happen? They will be randomly moving all around in the space provided. Okay, so they will possess energy by virtue of their motion, which is kinetic energy. So all these particles will be moving randomly at room temperature. So the energy that is possessed is kinetic energy, and it is quite impossible to calculate the kinetic energy of these randomly moving particles also when they are 6.023 into 10 to the power 23 in number. So what do? We take average. So we take average of kinetic energy. Okay, all the atoms, we take the average, and then that average number is referred to as temperature. Okay, so the average motion of these particles, okay, in a substance is referred to as a temperature. Now the next thing we want to learn, is about chemical systems. So what is a chemical system? It will have a group of reactants and products. Okay, so chemical system will consist of a group of reactants and products. Okay, um, so let's say you have some things going on here. Okay, you have a chemical system, and this thing is enclosed in water. Okay, and then this system is locked from outside. Okay, let's say this is some insulated shield around it, and there is water here. Okay, now I will tell you. This water is referred to as the surroundings. This is water, and this is equal to surroundings. And then this system, A plus B giving you C plus D, then this is the chemical system. Okay, this is the chemical system. Now, there are many types of systems. There are essentially three types of chemical systems. One is open system, second is closed system, and third is isolated system. So for open system, what's the condition? It is a system in which both matter and energy are free to enter and leave. Okay. For example, this is for example, you have a hot cup of coffee and there is no lid on the top. Okay. So you have this cup of coffee and there is no lid on the top. So what will happen? So the coffee as well as the heat from here, the energy from here can be freely exchanged with the surroundings. This type of system is known as open system. Now the closed system, what is the criteria for this one? This is a system in which energy can enter and leave. So energy can enter and leave. However, matter cannot. So matter cannot. So for example, now on this cup of coffee, you place the lid or you try to close it with anything. Okay, so there is a hot cup of coffee. So what will happen? Energy can be exchanged, it can enter and leave, but the matter is still intact in the cup of coffee. So this type of system is referred to as closed system. So what is the isolated system? So you must be aware now. Here, no neither, let's write it in this way, neither matter nor energy can enter or leave the system. Okay, so neither of them can, you know, can leave or enter. So, for example, you have insulated flasks these days, okay, with insulated lids. So let's say you keep hot water inside it. So they claim that the temperature will stay constant. However, it cannot stay constant for like lifelong, because this is a practical world. Nothing is idle here. So it will have some shortcomings. So energy will find the way to exchange or to enter or leave the system. Okay, but however, it will stay warm for a longer period of time. So this insulated flask or insulated cup is a example of the isolated system. Now, moving on, we want to study now these chemical systems, and under those chemical systems fall reactions. So, reactions can be endothermic, they can be exothermic. First, let's study about exothermic reactions. Okay, so exothermic means releasing energy to the surroundings. This is what we want to understand, releasing energy to the surroundings. For example, you try to burn a gas. For example, this is a methane gas. You're trying to burn it in the open air. It becomes carbon dioxide, water, and some energy is released. So this is an example of exothermic reaction. This is an exothermic reaction. Okay. So what is happening here? Energy is being released, okay, to the surroundings. Now exo means out of, so I will write here exo means out of, so energy is released out of the chemical system. Okay, now if you see a graph here, which is potential energy diagram. If you have potential energy on the y-axis, then how do your system looks like? Let's say you have here your system. Okay, this system consists of your reactants CH4 and oxygen, and it consists of your products, which is carbon dioxide, water. Okay, so what is happening here? There is an energy difference here between these two reactants and this products. So there is energy difference here. So energetically, your reactants are higher in energy as compared to your products here. Okay, and energy is being released to the surroundings. This is the surrounding, so I will write energy released to the surroundings. Now the next thing we want to learn about is endothermic reactions. For endothermic reactions, so they are quite the contrary. So endo means inside, so I will write here endo means inside. So you might be guessing now. So this is a reaction that absorbs energy. So absorbs, so reactions absorbing energy from the surroundings. Okay, so here what will happen? The opposite will happen. So they will, the energy will flow from the surroundings towards your system. So this is your system here. Okay, consisting of reactants and products, and this is the energy difference between them. Now I'd like to give you an example here. For example, N2 gas and oxygen gas, and if you give them some energy, they will become product which is 2NO. Okay, so here energy is on the reactant side. Here you are giving energy to the reactants. So they are energetically means they are low. You have to give them energy so that they can be converted to products. Okay. Now for these endothermic reactions, if I want to plot the graph, how does the graph look like? So this is the potential energy axis. Okay. Now I already told you. So these reactants are low in energy. That's why you need to add energy. You need to give them energy. So you will make your reactants lower here, N2 and oxygen. Okay. So these are the reactants. And then somewhere here will be your products, which is NO. Okay. Which is NO gas. Okay. And this is the energy difference between them. So if this is the energy difference, let's say this is delta E, okay, and then this is your chemical system. This whole of the stuff is your chemical system, and energy will be flowing inside. So I will write energy absorbed from the surroundings. Fine. Okay, now since we learned about endothermic exothermic reactions, so now the next thing we want to learn is heat capacity. Heat capacity, whose symbol is lowercase c. Okay. Now the thing we want to learn about in this topic is basically it is specific heat capacity. Okay, so I will write here specific heat capacity. So what do we understand by this term specific heat capacity? The quantity of thermal energy, I will give you an example so that it is more clear. The quantity of thermal energy required to raise the temperature of 1 gram of a substance by 1 degree Celsius. And can you predict what will be the SI units? SI units will be the amount of thermal energy required, that is measured in joules per gram of the substance to raise the temperature by per degree Celsius. Okay, so this is the units joules per gram per degree Celsius. Okay, now for example, you are on a hot beach, you are on a beach on a summer day. Okay, now what will happen? There will be sand, okay, and there will be water as well. Okay, so let's say this is your water and this is your sand. So there is sun here, it's a bright sunny day. So both are being heated by the same source, which is sun. So what will happen? So when you will try to walk on the sand, it will feel too hot to walk. However, when you will go into the water, it will be not that hot. You can stay calmly there. So what is the difference? Because they are being heated by the same source for the same amount of time. Okay, but one is very hot and one is cool, is comparatively cooler. The thing that is making the difference is your specific heat capacity. Here you want to learn about this specific heat capacity. So this is a property characteristic of substance, different substances have different specific heat capacities. So here, what makes the difference is this C. So here sand, for sand, if you take 1 gram of sand, to raise the temperature of 1 gram of sand by 1 degree Celsius, you require lesser energy. You require lesser energy. So it's easily heated. However, for water, here you require more energy to heat 1 gram of water and to raise its temperature by 1 degree Celsius. Okay, so water requires more energy to do the same thing, to raise its temperature by 1 degree Celsius, as compared to the sand, which requires lesser amount of energy to raise its temperature of by 1 degree Celsius. Okay, so I'll try to give you some more insight by writing some values here for specific heat capacities of some common substances. For example, your substance is liquid water. So water is not always liquid. It can be found in solid and gaseous forms also. So what is the specific heat capacity for liquid water, the water we drink? I will write C here. And then in the bracket, I will write the units, which you are quite familiar now, joules per gram per degree Celsius. It's 4.18 here. For ice, it's water in the solid form. It's 2.03. And let's learn about aluminium, whose specific heat capacity is 0.900. Okay, so these are the amount of joules you need to raise 1 gram of this substance, okay, the corresponding substance, the temperature by 1 degree Celsius. And let me write one more. For example, for iron, it's even low. You just require 0.44 joules to raise the temperature of iron by 1 degree Celsius. Okay, so 1 gram of iron, if you want to raise its temperature, you just need to give this much energy. Here, for water, you need to give 4.18, okay, joules of energy to raise the temperature of 1 gram of water by 1 degree Celsius. I hope you understand. Now, based on this, how do we measure these values, these energy exchanges? So here we want to learn about calorimetry. So slowly we are going into the depths of thermochemistry. So calorimetry, it is the experimental process. What is calorimetry? It is the experimental process of measuring the thermal energy change in a chemical or physical change. So this is what thermochemistry is, right? It is a study of energy changes that are involved in chemical or physical changes. So the experimental process by which we measure all these things. So how do we know it's 4.18? Do we know it's 0.44 for iron? So calorimetry is the experimental procedure to do that. And calorimeter is a device that helps you to do the same. So calorimeter, a device that is used to measure thermal energy changes in physical, I will just write PHYS, physical or chemical changes. So for chemical, I will just write, okay, let me write full chemical changes, okay. So the device which will help you to achieve the measurement of energy for these reactions. That device is known as calorimeter. Okay. Now there are three types of calorimeters. First is, so I will write here types of calorimeter. So we are slowly going into the depths of thermochemistry. So first is a coffee cup. Okay. Coffee cup calorimeter. So you just take a glass of, let's say, a one-time usage glass. You find the plastic ones, and you put the lid on the top. Polystyrene cups. Polystyrene is the material here. Okay, for both the lid and this, and then you insert the thermometer inside it. Okay, and then you have, let's say, some stirrer here with which you can mix the liquid here or whatever chemical system you have. And this is one way to measure the energy changes. You'll see the temperature difference here on the thermometer, and then you can note the energy changes values here. And then you can calculate from here, from the temperature difference values. The second is laboratory calorimeter. So I will just write lab calorimeter. So here you will have some finer material. Okay, and then you will have some insulated lid on the top, and then you will insert thermometer inside it. Okay, and then it will provide more precise data as compared to your previous one. So more precise data you can achieve from the lab calorimeter. This is again the thermometer. You can measure the temperature values here. And the third one is known as bomb calorimeter. To study about them in details is not the aim of this online lecture. So we are not going into much details, but just introducing you to them. So this is a bomb calorimeter. Here you can measure gases also. Okay. So it is a fine calorimeter designed nicely. You can check them on the Google also. And then there is thermometer here. Okay. Inserted, and some other pieces to make sure there is no interaction of the system with the surroundings. And then this is your another type of calorimeter. Here it can provide precise data, the most precise data you can achieve here for any changes of state. It involves gas also, so neither of them will study about gases, but here you can study gases also, involving gases as well. Now moving on, we want to do some questions based on what we have done so far. So we will do some calorimetry calculations. So for the investigations of thermochemistry in the textbooks, we will assume that we use coffee cup calorimeter. Okay, we use coffee cup calorimeter for investigations for this course. So we make some assumptions here while doing the calculations. We make some assumptions. So what are those? Number one, because coffee cup calorimeter is will not be that good in preventing the energy exchange. So any thermal energy transferred from the calorimeter to the environment, okay, to the surroundings, is negligible. So this is not an ideal word, but we try to make it in calculations. So we will assume that if this is a coffee cup calorimeter and we are trying to study any system for the purposes of this textbook, we will assume that the energy exchanges between the system and the surroundings, even if they are happening, they are negligible, they will not disturb our actual calculations. And the second assumption is this: any thermal energy absorbed by the calorimeter itself is also negligible. Okay, so this is a coffee cup calorimeter. This is made up of some material. We told you it's polystyrene. So when you pour some hot system, let's say, so it will also try to absorb the heat. Okay, so some heat will be absorbed by this material also, the material with which your coffee cup calorimeter is made. And for the sake of idealization or for the sake of calculations, we assume that even if there is something absorbed, that something is negligible. So the energy that is absorbed by this material is negligible. And the third thing, and the most important, all dilute aqueous solutions have the same density as water, okay, have same density and specific heat capacity, which is 4.18 joules, I told you in the table as well, per gram per degree Celsius as water. Okay, so all the dilute or aqueous solutions, they have the same density. So all the liquids, whether it's any liquid, we will treat them as water only in our all the calculations. Now